Hello, and welcome to your final video on understanding phase diagrams. And here we're going to move on to the final details you need so that you can understand the phase diagram for steel. To do that, we first have to understand the partially soluble binary phase diagram. And you might say, wait. I know soluble and insoluble, but what does it mean to be partially soluble? Basically, if you're partially soluble, your two materials at a certain percent composition can be soluble, but once you exceed that percent composition, then the composition behaves like an insoluble material. Let's give that a little bit more explanation. So let's just say you have mostly material A and you have a little bit of material B. So that's great. As long as your quantity of material B is below the solubility limit, then material A, when it solidifies, just holds the atoms of material B interstitially. And basically what you end up with is material A. It still considers material A and the behavior does not change. If your percent of material B is over the solubility limit, then B cannot be held interstitially in A, and B will solidify in its own material and create its own grains, and your final solid is a composition of solid A and solid B, just like the insoluble phase diagrams, and you would read the diagram as if it were an insoluble phase diagram. So let's take a look at then the partially soluble diagram. So we still have our liquidus, and our solidus just changes a little bit, but we still have our solidus, and we still have a eutectic point. And now, if I have a material that is mostly A, and it starts solidifying, we can see that when we get all the way down below the solidus and we have a liquid, we just consider it material A or material alpha. It's slightly changed from true A, but it's just holding a little bit of B interstitially, and so we treat it as if it's just the original material. Its properties are not changed. Instead, if we had too much of material B and we were over the solubility limit, then as the material cools and we get below the solidus, then we just have solid A and solid B interchangeably held together, just like we learned in the insoluble phase diagram behavior. Now, our steel, which is made from iron carbide and carbon, is a partially soluble material. And so this is actually the phase diagram that we would use for steel, or iron carbide carbon. So here's our liquidus. Here's our solidus. We even have our eutectic point. But suddenly below the solidus, where we're supposed to just have solid material, we suddenly have all these other lines happening and all these other things. So what's going on here? Because this does not look like a phase diagram we've seen before. Well, to understand this, we have to introduce the idea of allotropes. So some elements are able to exist in different forms, even though they have the exact same chemical makeup. It's just they have a different chemical structure, right? And all the different forms are called allotropes. So what we mean by this is carbon. Carbon is the perfect example for this. Carbon has 8 different allotropes. 3 well-known allotropes of carbon are going to be diamond, graphite. That's just the stuff in your pencil lead, so it's very soft compared to a diamond. And then graphene, that new high-tech material everyone's talking about. Another one's called zigzag. Check it out. But even though these all are carbon and the exact same chemical makeup, their structure is different. Well, iron is the same. Iron actually has 3 of its own allotropes. One is high temperature ferrite, or delta iron, and it is a crystal lattice of body-centered cubic unit cells, but it only exists at very high temperatures. Austenite, or gamma iron, actually has a face-centered cubic structure, and this exists below 1500 degrees Celsius, about that, and as low as 727 degrees Celsius. And then our final allotrope is low temperature ferrite, or alpha iron. This is, again, body-centered cubic unit cells, and it starts forming at about 912 degrees Celsius, and then once you're below 720 degrees Celsius, all iron is alpha iron, or this low temperature ferrite. So when the iron transitions between its allotropes, the crystal microstructure actually has to change, right? We saw we could be face-centered cubic or body-centered cubic. The point where the microstructure of the material actually changes is a function of temperature, at least for iron, and that point is called the eutectoid point. And it turns out that if we're looking at a phase diagram, the eutectoid point is actually really similar to the eutectic point that we learned about in insoluble phase diagrams, where we transition from our combined liquid solid 100% to solid. Well, the eutectoid is similar, the rules for reading the phase diagrams are the same, and so you might have, say, at 850 degrees, both austenite, or gamma iron, and low temperature ferrite are alpha iron, but as soon as you get to the composition, as your alpha iron amount is changing in the composition, and as soon as you get to 727 degrees Celsius, everything transitions to alpha iron, or that low temperature ferrite. So here's an example of the eutectoid reaction and a generic diagram, not even looking at steel. So again, we'd have a liquidus, we have our solidus. That doesn't change. Now, let's say we had a material whose composition was almost all material B. So on this particular diagram, we are still partially soluble, and as the material cools, it would just become this material B holding material A in its atomic structure interstitially, and it wouldn't change what material B is. But if we tried to do that over with our material A, what we would find is that as we start cooling from the liquid form and pass our solidus, we actually turn into this gamma structure, but as we continue cooling, some of the gamma turns into alpha, and then as we cool even more, it 100% turns into alpha. And so we're changing our form, but if we were in the middle, somewhere in the insoluble range, where we had too much of material B, when we hit the liquidus, only material A would start transitioning to a solid, but it would transition into gamma material until we started cooling more and more and got below our solidus, and we'd start to see that we could have some beta forming in the solid, but then some of our gamma would transition into alpha until we got below a certain temperature, and then all the gamma transitions to alpha. And so we actually have this whole range here that we've just highlighted that is our solid state transformation. You may have heard that expression, solid state transformation. So we're in a solid form, but as the temperature changes, our state transforms, and we can go back and forth between alpha and gamma. So we may actually take alpha and raise the temperature to turn it back into gamma. So we can go in both directions. And the eutectoid point, we can actually see on our plot, is this lowest point that our gamma could exist before everything transitions to alpha. Just the same, we have a eutectoid composition, so how much beta is left, or material B and material A is in the composition, and it occurs at a set temperature, so we'd have our eutectoid temperature, very much like the eutectic point. So we can actually now look and see what would this look like with steel. So this is a phase diagram for iron and carbon, so you create iron carbide and carbon, and let's just highlight some different things on this diagram. So we have the three phases of solid iron. So iron can be high temperature ferrite. We said delta, and we can see it's up there at those really high temperatures. Now this has really no practical significance in civil engineering. Then we have austenite, and that's our face-centered cubic, and we see that cools when we start cooling below where the high temperature ferrite can exist. And then we have our low temperature ferrite there below 727 degrees permanently and starting around 912. Now you might say, well, austenite also really shouldn't be of practical significance in civil engineering because it's at 727 degrees Celsius, which is not a day-to-day temperature. The thing is that the austenite is really good at dissolving carbon, much better than ferrite. It can actually hold carbon interstitially at over 2% carbon interstitially, and so we can heat back up steel and have that carbon move into the austenite, and then depending on how quickly we cool the steel, the carbon can or cannot quickly leave and disperse, and we can actually change our crystal structure. And we're going to learn a lot more about that when we get into heat treatments. Now, some more things about the phase diagram we will use to understand steel. We still have a liquidus. We have our solidus. We have our eutectic point, where we transition from liquid to 100% solid. But now we also have our two eutectoids, and these are the points where we transition the upper eutectoid from high temperature ferrite to austenite, and then the crystal structure changes at our lower eutectoid down to our low temperature ferrite. We also have the solubility limits. So we've said that austenite can hold more carbon, and it holds about 2.1% is that solubility limit, where it can actually just hold the carbon interstitially between its face-centered cubic unit cells. But we mentioned a while ago that the solubility limit of iron, and really the alpha iron, is only 0.022% for carbon. So it really can't hold much interstitially. And below that percent, or any carbon up to that, we treat this as partially soluble. So anything below that 0.022% is just considered to be iron, whether it has carbon in there or not. We do have the lower critical and upper critical temperature lines, and these are just the temperature lines where we do start transitioning into our alpha and also iron carbide. Those we're not as concerned about. But it is important to note down that 6.7%. That is the maximum you'll ever see on this diagram for percent of carbon. We won't go up to 100% because once we have more than 6.7% carbon by weight, you just get 100% iron carbide or cement type pure cast iron, which is so brittle, it's just not a useful material that anyone would ever use. So we are not even interested in what's happening above that weight. All right, finally, a couple more things to point out on this diagram. When we get down below the 727 degrees and we have then our ferrite iron, or our low temperature ferrite, and our cementite or iron carbide, we've said that these both form as individual solids because we're insoluble, and we've already seen the grain structure, and in reality that layered structure, which we again have said is our ferrite and our iron carbide, we're going to call that pearlite. When we get those nice thin layers, that pearlite shares the ductility of iron with the strength and hardness of iron carbide. And we're going to learn more terms like pearlite for different ways that the ferrite and the iron carbide can disperse with each other depending on the cooling rate. So that's your introduction to the steel phase diagram. We've said steel sits at about 0.15 to 0.3% carbon, so much lower than this plot goes to, or this graph goes to. But it's very important that we understand the austenite and the low temperature ferrite possibilities because it will affect the strength of our steel. Thanks for watching.